Recording is on.
Yep. Hi, everyone, and thank you for joining our call today. And Maxim, the stage is yours.
Yeah, hi everyone once again. Today I'd like to do an overview presentation about RGB smart contracts. While it's overview presentation, it'll still be a bit combining both deep diving and some technical details with some high level overview. My goal is to explain the current state of what we call RGB as a system in terms of both computing science and some convenient logic, and show how different parts of RGB and underlying technologies, which we were discussing on many previous calls, stick together to form overall RGB computing. And most of the presentation will be also about the RGB computational model, which we call PRISM. It's a sort of abbreviation coming from partially replicated indeterministic state machine. And I will be explaining why it is named so and how basically it works. I would like to start with the high-level stuff, explaining what is RGB. And RGB is, in fact, the first client-side validated smart contracting system. Maybe there will be more later client-side validated smart contracting system, but up for now, it is the only smart client-side validated smart contracting. And to explain that, probably I need to start with what is client-side validation first, because what makes RGB special. Comparing to other smart contracting systems. Client-side validation is a distributed computing operating on layer 2 or 3, but still using layer 1 for state verification. And this is, in fact, true for any layer 2 or 3 applications, because all of them are relying on the consensus properties of layer 1. And the client-side validation is both an alternative as layer 2 or an extension, if it is operating as layer 3, to state channels like lightning channels and other forms of state channels. So it's a kind of another vertical of how you can compose more functionality, programmability, and scalability on top of blockchain. And the term client-side validation was coined by Peter Todd as a logical extension of his work on open timestamps. And again, I would like to clarify that the client-side validation is not something that can be, you can't name everything client-side validation that is above all the blockchain. It's have very specific meaning. And we have to differentiate the client-side validation from client-side data. So for instance, in Bitcoin, with a pay-to-script hash scripts, or if we are talking about the new coming taproot scripts, the client still have to keep the script source code. So he has to keep the data on his side, and these data are not part of the blockchain, at least until he spends the script. And with a taproot, even if he spends the output, the whole script doesn't become a part of the blockchain. So there is some data kept by the client on his side, so client-side data, but it is not a client-side validation. The same with the taproot. If you are using multi-sig scheme called music2, you need to keep some additional data which are not script data. These data are used to generate the information about multi-signature. And this client-side data and client-side state, it is not a client-side validation system. Or, as I already said, state channels, which is an alternative to client-side validation. Lightning Network, discrete log contracts, they require you to keep the signatures or the transactions for off-chain transactions, which are not published to the blockchain, neither signatures or transactions. And you have to keep them on the client side as a client-side data, but again, it is not a client-side validation. So what is client-side validation? Client-side validation is when you validate some client-side data against certain rules. And these rules must include blockchain-based commitments, like timestamps or single-use seals. So if you are not using blockchain-based commitments, if you're not using timestamps, if you're not using single-use seals, and you just have a client-side data which are not validated against blockchain, it is not a client-side validation. It's just a client-side data. So it's quite important to differentiate these two things. But wait a minute, I'm already talking about state channels, not about just the Lightning Network. And I'm saying that client-side validation can be put on top of state channels or as an alternative to state channels. But what are state channels outside of the scope of Lightning Network in these terms? If we speak about client-side validation as a state validated against client-side data and state validated against blockchain, what is state channels? Well, the state channels are a different form where you maintain certain transactions off-chain, Bitcoin transactions off-chain, and plus some number of signatures. And these state channels, today we know at least 4 cases of different state channels on top of Bitcoin. The only working solution is the Lightning channels, and this is a payment solution and a payment network using state channels. Pretty much ready to go are discrete block contracts, which will become much more capable when the taproot will be activated. It is an Oracle-based future contracts utilizing scriptless script concept. And 2 very early stage ideas and concepts are Storm and Prometheus, which are also actually proposed by LNPBP Association and myself, which the Storm is a escrow-based trustless storage using zero-knowledge proofs, and Prometheus is arbitration-based trustless distributed computing system. And both of them are form of a state channel. And the interesting property of state channels that you can compose and put one type of state channels on top of other type of state channels. For instance, you can put discrete block contracts over Lightning Network, and you can basically build layers of state channels on top of each other. So that is what state channels are. But how they are compared to the client-side validation, in which way they are different, and what are trade-offs when we talk and select between these two. So here on this slide, I will try to highlight the similarities between these two ways of building layer on top of blockchain. The similarities will be shown in blue color, and the differences, which can be neutral in cyan color, negative in red color, or positive in green color. So state channels, they work with blockchain and sometimes other state channels. As I just said, like you can compose state channels on top of other state channels. In client-side validation world, you can work with both blockchain and any other state channel. So if there might be a possibility of composing one state channels with other state channels, there could be many cases when you can't combine different types of state channels. There is no trivial or universal way to combine, to put one state channels on top of other state channels. With a client-side validation, it is always possible. You can take any state channel, Lightning Network, you can take discrete block contracts, and you can put a client-side validation layer on top of them. So client-side validation always can extend any state channel solution. State channels are synchronous, meaning that all parties performing some action with a state channel have to be online. And while client-side validation is asynchronous, and it means that it is resistant to network failures. You can initialize operation in offline mode, and you do not require, while you still may need interactivity, you don't require all peers to be online, and the operation can be completed in asynchronous mode. State channels may require routing, not always, but the most common example is the Lightning channels, when you need a routing to route the payment. And routing creates its own problems because basically you have to compute routes, you have to maintain the whole map of the whole network. It imposes certain scalability issues. With a client-side validation, you do not require routing. However, unlike state channels, you may require storage providers, meaning that if their protocol operates in a synchronous mode and one party is doing some state transition for other party. The other party is beneficiary of this state transition, and the other party is not online. There should be a certain interactivity protocol where the receiving party, when it becomes online, should be able to access the data created a sending party. So it should be either a storage provider, which can be part of the decentralized network, like Lightning Network, or there should be interactive protocols between a receiver and sender. So in this parameter, the state channels and client-side validation have a different trade-off. So state channels usually require routing, and client-side validation usually requires storage. State channels, both of these use client-side data, but state channels uses client-side data as signatures or transaction. Sorry, there is a small mistake here. We'll be on the next slide. State channels, they have a client-side data as a form of signatures of transactions, while client-side validation can maintain any form of complex state on the client side. However, as a result of this, the size of the client-side data in state channels is tiny because it's just a signature, or at most is a transaction, while on the client-side validation part, you can have a huge size of client-side data. The security of state channels may require watchtowers. Well, actually, it always requires, because if you are going offline, you may be scammed by the other parties. So you have to maintain some part of the network operating online and monitoring on-chain events. So that's called watchtower. On the client-side validation, there is no watchtowers required, of course, unless you compose a client-side validation solution on top of state channel. And then, of course, you will require watchtower, but not because of the client-side validation, but because of the state channel part. And finally, there is no state validation when you operate with the state channels. So that's why they are not client-side validation system. And client-side validation always perform certain state validation actions additional to blockchain-based mining and transaction validation. So that's the difference between the two of them. And the RGB as a smart contracts using client-side validation basically utilize and can be layered on top of two systems, blockchain or state channels. And state channels are always based on security of blockchain. And with the RGB, you have an owner or contract participant who holds some certain client-side data, which we call stash in RGB. And he verifies proofs coming from the stash against both blockchain or state channel, which is again verified against blockchain. So the whole security model of client-side validation is based on the security model of blockchain, as much as the security model of state channels is also based on the security of blockchain. The fortunate part that there is no on-chain analysis possible. And from blockchain data, you can't anyhow suggest anything about client-side data. Unlike state channels, where you may do an on-chain analysis of certain typical cases and track that this specific transaction was related to a certain form of a state channel. With a client-side validation, no analysis of that kind is possible. Well, not with all kinds of state validation. Of course, you can create client-side validation protocol that allows on-chain analysis, but in particular case of RGB, it is designed in a way that there is no possibility of any on-chain analysis. So why client-side validation? Why we need all of that if we already have Lightning and state channels? Well, there are 4 reasons which I can name, and 2 of these reasons makes client-side validation better than blockchain, and 2 other of these reasons make client-side validation better than state channels and blockchain. So the first one, you will get more confidentiality. So you have much more ability. the structure of the transactions which you publish on the blockchain do not need to be anyhow customized to support client-side validation. Unlike with the state channels, when the structure of the transactions usually have to be specific and will contain a fingerprint of the state channel type. For instance, if you will publish if you do a non-cooperative Lightning channel closing, it will be quite clear from the blockchain that this was a commitment transaction of a Lightning channel, or this was an HTLC of a transaction of Lightning channel. Or the same will apply for DLC contracts. With RGB, the structure of the transaction can be any, and there is no fingerprinting happening there. Also, because you store the whole state on the client side, unlike with the blockchain and unlike with the state channels, the whole state is kept client side, and there is no single part of state that is reflected on the blockchain. The second point is that you gain more scalability comparing to blockchain, at least in terms of the size of the state data. So with a blockchain, you are limited by the size of the block. With the client-side validation, this limitation is removed. So you gain storage scalability. Next, you have more programmability with the client-side validation. And you get more programmability both comparing to blockchain and state channels. Because again, you have a rich state and add additional scripting systems, virtual machines, whatever you need. And that actually unlocks the whole potential of smart contracts. And finally, you have a richer state data, again, because you are not limited in size of your client-side data, and you can structure them arbitrarily. And that is the final pro about client-side validation comparing to blockchain and state channels. Now, how we can structure different client-side validated systems and where RGB takes part in that structure. Probably, from what we know today, and it's very early days of client-side validation, it's basically just several projects being related to client-side validation since the term was coined by Peter Todd, and probably in the future we will invent some other forms of client-side validated systems. But today we can classify all client-side validated systems into two categories. The first one is a timestamp based, and for Bitcoin world, I know the only one main timestamp protocol, which is Open Timestamps, developed by Peter Todd and others. And the second category is single-use seal-based systems. And in this category, the main example, and mostly only example, is RGB, smart contracts. But there are clear ability to build more, to construct more case-specific single-use seal-based systems like Schnorr signatures and decentralized identity based on Bitcoin blockchain. It was a proposal from Bitcoin mail list. There is an URL link, you can read about it. So that's a way how you can use single-use seals and client-side validation outside of the scope of RGB. So I expect that there will be more proposals and ideas appearing and emerging in this sphere, such that client-side validation will grow much bigger than just an RGB smart contracts and open timestamps. So RGB client-side validation is similar to timestamping, but more complex. It allows verification of the unique histories using single-use seals mechanics and not just a single state, like with the open timestamps. So for those who like to understand how these single-use seals work and how they are different from timestamps, I advise to watch this presentation. Here are two links for the slides and video recording. So putting all of this together, when we talk about distributed systems in context of Bitcoin, we can say that there are at least 3 blocks with different properties. There are fully replicated systems, which are usually called blockchains, but I try to avoid this term. And in terms of replicated state machines. I see at least three important categories, which is proof of work, time chains, Bitcoin itself, BFT-based databases. Somebody names them blockchain or proof of stake blockchains, but again, in Bitcoin, unfortunately, don't have that chip. And that's why I just said that there might be some applications for Bitcoin world for BFT-based database solutions, but we don't have them one yet. And maybe we will not need them. And the final example are federated blockchains like Liquid, and they differ from both proof of work and BFT systems because you have you have a very simple consensus protocol, which is basically a proof of authority consensus protocol. The second big category of distributed systems in Bitcoin world are the state channels, which are non-replicated state machines. And these state channels, as I already mentioned, include such channels like Lightning channels, DLCs, Storm, or Prometheus. And the final third category, introduced by client-side validation, consists of timestamp-based systems and single-use seal-based systems. And among single-use seal client-side validation, the main topic of today's discussion is the RGB smart contracts, which represents a partially replicated machine. I will be talking about what it is in a moment from now. Another way of putting it all together, this thing that we call LNPBP stack, Lightning Network Protocol and Bitcoin Protocol stack, is this diagram representation where we have a Bitcoin blockchain at the bottom layer, let's say like that, side chains sticking in between, and state channels we can utilize and run both on top of Bitcoin blockchain or other side channels. And there is a client-side validation world, which comes on top of all of these three. And we basically can run a client-side validation type of solutions, both on Bitcoin blockchain directly or using sidechains, like nothing prevents you from doing open timestamps with a Liquid, or on top of state channels. So that is probably the most complete explanation of how these layers are related. But of course, it's very different from what is usually said as layer 1, layer 2, layer 3, because it's really hard to distinguish here where is the layer 1, what is the layer 2, and what is the layer 3. Sidechains, are they layer 2? Client-side validation, is it layer 2 or 3? When it is put on top of state channels, it's probably layer 3. When it is directly working on top of Bitcoin blockchain, it's clearly layer 2. So there is a lot of ambiguity, and I'm not sure that there is a very clear and straightforward way to avoid this ambiguity. But one of the proposals which we may follow is that Bitcoin blockchain is certainly layer 1. There is no doubt. And state channels, they're certainly layer 2. Also no doubts. So maybe we can assign the side chains representation as a layer 1.5 and client-side validation as layer 0.5 with the layer 3 solutions, which are basically will be utilizing client-side validation or state channels being based on top of them. So that's maybe the way we can stick all these layers together. And the most important part is that we do not have to select between using state channels and client-side validation. When I was doing this comparison of the state channels and client-side validation, we've seen that they have different trade-offs, and we are not obliged to choose one of them. We can use the best of both of these worlds. And like you can put one state channels on top of others, in some cases, like DLCs over Lightning, we are fortunate that in all of the known cases, and I think this can be formally proved, you can always put a client-side validation on top of state channels. And while it may require customization of the state channel protocols, it is quite a big benefit because basically you can gain, in this way, you can gain both scalability in terms of size and speed. You can get much more confidentiality, and you can give a lot of programmability to both Bitcoin blockchain and Lightning Network. So that was all about a general overview of client-side validation. And now I'd like to dig into details about RGB, about RGB as a specific form of the client-side validation. So let's move from the client-side validation to explanation of what RGB smart contracts is and what is their place inside the client-side validation world. So we can think about RGB smart contracts as directed acyclic graphs. And I can say that each RGB contract can be represented as isolated DAG. So it's not like there is some RGB, which is a network or a distributed computing system or whatever else. RGB do not exist as a whole. RGB is a set of protocols. And unlike blockchain, Lightning Network, Ethereum, or any other of existing smart contracts systems where the whole state is maintained by a big distributed container, like blockchain in most of the cases, or as a peer-to-peer network, like in Lightning Network, RGB is very different. There is no single system, and there is no mainnet, testnet, or whatever. Each RGB contract is a system in itself, fully and completely isolated from other RGB contracts. So when you create an RGB contract, nobody else other than you knows about that until you invite more participants into this contract. So that makes the system very robust, confidential, and actually scalable. And that's why each RGB contract is an isolated, directly acyclic graph. Theoretically, we can call RGB contract a shard. I'm not 100% sure that it is correct from the computer science perspective, but the word is anyway abused in the smart contracting world. So at least it will help people to understand comparison of RGB to other smart contracts. So each RGB contract is a DAG of state transitions. We call them RGB nodes, actually, because it's not only state transitions. There might be other types of nodes. We will be talking about that in more details a bit later on. So it's a DAG of certain nodes, and only tips of this DAG contain active state. The rest of the DAG is a history. And if you compare this to blockchain, there are quite a lot of similarities because if you think about transactions inside blockchains are also a DAG. And only tips of this DAG, which are actually UTXO set, contains the actual state distribution, the funds distribution, and the actual state of the blockchain system. The rest of the blockchain is just a history record. So pretty much the same applies for RGB. But unlike in blockchain, RGB state transitions and contract nodes are not packed into blocks. They still exist as a DAG. There is no need to pack it into a blocks. And instead of packing it into a blocks, RGB uses a special mechanism called anchors, which anchors the RGB contract nodes to specific Bitcoin transactions residing inside blocks, residing inside mined blocks. And that's how we are leveraging the power of proof of work consensus of Bitcoin blockchain and anti-double spending prevention by Bitcoin blockchain to build another graph on top of it, maintained completely separately from blockchain itself. So that's the trick. We use anchors basically to build a much richer state and much larger DAG, which is specific to a certain smart contract. It is not generic like blockchain itself. It is completely confidential and much more scalable, but the same secure as blockchain itself. So that's the trick with the client-side validation. And it is the fact that the anchoring mechanism, because you can link multiple transitions under multiple RGB contracts to the same transaction. There is no limits how many, well, there are certain limits, but still it's very scalable. We are talking about tens of thousands of state transitions, which may be linked to a single Bitcoin transaction output. And because of that, the anchors, they are basically a link in between the world of RGB contracts and blockchain. and anchors link multiple RGB contracts to the blockchain. This doesn't cancel the stuff that I said about RGB contract isolation, because in terms of state and computing, they're fully isolated from each other. The anchors linking is only about a cryptographic commitment when you talk about hashes, and from that hashes, you can't deduce any state. So it's pretty much the same hashes which you use to trick the public keys in the blockchain, and that don't contain any valuable data. It's basically a noise and an entropy from informational perspective. So that's how it looks like. And the security model, as I said, it is based on the blockchain. I will try to simplify how it works. There is always an owner of some certain state, not the whole state of RGB smart contract. The whole RGB smart contract state is separated into atoms, small pieces, which we call assignments. It's assignments of a state to a certain UTXO or a certain single-use seal. That's why they're called assignments. And each assignment has an owner. And the owner of this assignment, of this assigned state, is always the same person who owns private keys from the UTXO, which is assigned this specific state. So we have an owner who is actually a contract participant, because all owners are contract participants, and each owner keeps and holds the client-side data, which in terms of RGB we call stash. And this client-side data, as I already said, consists of a DAG of contract nodes, starting from contract genesis. On the other side, the same owner, he owns keys of a certain Bitcoin transaction output, which is mined inside of a blockchain or as a part of a valid Lightning channel state or other channel state, other type of channel. And linking this together, we see that the client-side data point to a certain unspent output by assigning certain state to this output. And until this output is not spent, this makes the state valid. Once the output is spent, the state got invalidated. And because you can't spend the same output twice, you can't invalidate the state in two different ways. Once you spend output, it is your opportunity to do a state transition, and you have just a one opportunity. You can't do two different state transition, changing the same state, updating the same state. That's how the security model works. So while all the client-side data, while all the state data are kept client-side outside of blockchain, we're still able to reutilize the security properties of blockchain. From a different perspective, once again, going through how the state transition work. If you plan to transfer certain state from one person, Alice, to Bob, what is the workflow of this procedure? Let's say Alice has a certain client-side data and owns keys from a certain Bitcoin transaction that has an assignment of certain state from this client-side data. And Bob has another transaction output, unspent transaction output, but nothing more. It's just a normal Bitcoin transaction output. And it's important to know that between these two transaction outputs and these two transactions containing these two outputs, there are no relation whatsoever. It's just like two random people owning different UTXOs without any shared history or any link in between them. And Alice wants to transfer her state, which can be tokens, funds, or some rights, ownership rights, or different forms of rights inside some complex smart contracts. So we are not limited to token shitcoins anyway here. And what Alice has to do is Alice has to do is to spend this output which contain that state. And for spending this output, she creates an arbitrary transaction. This transaction can return the funds in Bitcoins from that output to Alice once again. And there will be no relation whatsoever, again, between this transaction and the UTXO that is owned by Bob. And when Alice creates this transaction, he also needs to create a new state which will assign ownership right to the Bob by pointing into the UTXO owned by Bob. And the final part, she needs to create a zero-knowledge commitment, which will become part of the Encore, inside the transaction that is spending UTXO, which had a state owned by Alice. I understand that it's quite complex, but unfortunately, throughout 2 years, I haven't found a better way of explaining this. So probably if you're not grasping it, try to get once again through this explanation on the video recording or in the slides. And as the final part of this story, Alice has to pass this new state data with the state history to the Bob using some off-chain protocol. And from now on, Bob will have his own stash with the client-side data, including the state from that smart contract. And this client-side data, which are passed between Alice and Bob upon a transfer, called consignment or RGB consignment. We will be talking about these types of containers a bit later. So we end up with this story. And again, we have no on-chain analysis possibility because from on-chain perspective, where these client-side data are excluded, there is no relation whatsoever between any of these transactions. Alice just spent her output sending funds back to herself, for instance, or somebody else unrelated to Bob at all. It can be arbitrary transaction. Once again, the only thing that it needs is to contain a commitment to the newly produced state. And this commitment is cryptographically hidden as a zero-knowledge tweaking of public key in one of the spending transaction outputs. So hopefully this was clear. If it wasn't clear, I propose to ask the question straight away so I can reiterate and re-explain once again this part of the story. Okay?
Yes. So guys, do you have any questions? If you do, maybe let's take a break and ask.
Yeah, it seems like it was clear, so we can probably continue.
Yeah. So
next,
if in any case someone has any questions, feel free to just drop them in the chat, and then I'll just read it out loud when the presentation is finished. Don't be shy. Yeah, go ahead, Maxim.
Yeah. So how the client-side validation, how the validation part is performed for RGB. We validate ownership and we prevent double spending by reutilizing Bitcoin script combined with a single UCL validation. So again, it's I wouldn't fit the whole explanation into this presentation. So I really advise to check our client-side validation presentation dedicated to the single UCLs from this talk. Just give me a second. I will find, this one. So you can check this video. It's like 1 hour or more explanation of how single UCLs actually work and what is the security model of single UCLs. Next, the other part of the RGB validation is validation of the consistency and completeness of RGB data. And this consistency and completeness is validated using what we name RGB schema. It's a basically declarative description of how RGB DAG, the DAG of RGB contract nodes, should be composed. So that's what schema is. And finally, what you need to validate is you need to validate each change in the state history, each change of the state throughout the history. And you do that by utilizing AluVM, which is an algorithmical logical unit virtual machine designed specifically for RGB. And you can learn more about AluVM and its use in RGB by watching for another presentation that we had about a month ago. Again, I'm giving a link to slides and the video here. So it's high level. By going into details, I can say that there are three main blocks of the validation of the RGB contract. Again, the first one is the validation of internal consistency. And this validation made by checking that we can deserialize the provided binary representation of the smart contract data, and that we are provided with all the data that is necessary for the contract validation. So we know all the history of the contract. The second part, after we ensure that we have all the required information, is the verification of the state. And we verify for each of the contract nodes from the history and from the present state, we verify that the structure and the data inside that node match schema requirements and rules, the first step. The second state of the state verification is that we verify that each change in the state is valid under appropriate scripts, which are executed using AluVM, and all these scripts are part of either schema itself or contract genesis. And finally, after we verify the internal consistency of all smart contract data and state changes, we come to what I call Encore Verification, which is targeting prevention of double spans or double state transfers and transitions. And Arcane Verification again consists of two main blocks. First, we verify that all closed single-use seals are closed correctly, and we verify that checking against blockchain. Sorry, I forgot to say that Encore Verification is the only process, is the only part of the verification which requires access to Bitcoin blockchain or Lightning channel. So we check the transactions coming from Bitcoin Core and Lightning channel that they close single-use seals properly, all proofs are correct, and we verify that all of the transactions which are involved in the history are mined into the blockchain or part of the valid channel state, not the previous state, but a valid channel state. And by doing that, we actually perform the verification of the RGB smart contract. So from that, I can move to the final part of this presentation, which I will try to explain a computer science view of the RGB computational model. And you already see that the stuff with client-side validation and RGB, it's very different from what we have seen in the blockchain world and in the Lightning Network world. And basically, we will need to extend a bit boundaries of known in the computer science to describe the RGB computing model properly. So I will start with a brief recap of what computational model exists, what classes of automata exist, where the Turing computing stands there, because we constantly get a lot of questions, is RGB Turing complete, and so on and so forth. So to explain that, I will start with the basics. There are very simplified classification of the automata, basically forms of computing from the Wikipedia, when you can say that there is most generic Turing computing, Turing machine, let's say, like not Turing computing, Turing machine. There is more specific form of computing, which is push-down automation or stack-based machines. If we will narrow down that, we can get to the finite state machines, and finally we can narrow down that to combinational logic, which we wouldn't touch in this presentation. So in this presentation, we will touch finite state machines, push-down automation, and Turing machines. What are they? Let's start with the finite state machines, most specific type. Finite state machines include register-based virtual machines, like any modern microprocessor or simple controllers. And the finite state machine, the specific case of finite state machine, which is register-based machines, they operate by some head pointing into certain instruction inside the long bytecode of all the instructions and attached of the operands, of the operators and operands. And we have certain registers and each of the operations might modify register state. And we execute the program by just moving between these different operations and modifying register state accordingly. So that's what is a very simple explanation of a finite state machine in case of register-based computing. The second type of computing, more broad, is push-down automata, which basically are stack machines. And it is the way how most of the existing virtual machines are implemented. Additionally to input tape with the instructions, you have a stack, not a registers, but a stack. It's a variable size push-down data structure, and it works like that. So you move from one instruction to another, and some of this instruction may add data to the stack, so it grows, and some other instructions may remove the data from the stack, so it reduces, and that's how it differs from the rest of computing. And most, as I said, most of existing virtual machines used in the smart contracts, they actually use the stack-based, including Bitcoin script, EVM, PRISM, and others. And the final type of the most generic computing is a Turing machine. And what is Turing machine? Turing machine is described as an infinite tape, it's not type, it's a tape, infinite tape with a separate instructions from certain finite set of instructions, of all possible instructions. And there is certain head, like it's shown here on the right side, that is reading single instruction at a time. And depending on the instruction, it can modify its own state. So the Turing machine has own internal state. It can write to the tape basing on the instruction that is being read, or it can move throughout the tape to some other instruction. And that's way we can describe the most generic form of the computing. The machine, which was, of course, described by Turing himself, the design of this machine is quite inefficient in practical terms. So modern computers, they are not working exactly like Turing machine. There is no infinite tape. There is random accessible memory and other things which are absent from the Turing machine. But it is widely used, the description of Turing machine is widely used as an abstract reference model of universal automation, because it can be proved that any universal machine is equivalent and can be represented or restructured into a Turing machine. That's why we are saying that if we are having some universal form of computation, it is equivalent to a Turing machine or universal machine, and it is called a Turing complete computing. So that's the definition of what is Turing completeness by Turing is. And let's check RGB with all its validation and the rules against the Turing completeness. First, let's start with a description of how RGB computing model works. So we know now what computing models exist, and we know that the most generic one is a Turing equivalent computing, but there might be more restricted forms, and many register-based machines and finite state machines may be more, may be not a Turing complete. So let's check where RGB stands there. So if I will describe RGB smart contract computation model, we can say that, first of all, RGB as a computing is a distributed computing system because the state is distributed across multiple actors and participants of the contract state. And the distributed property actually applies, as we have seen, to all existing examples from blockchain and Bitcoin world, because I was showing here, all of these blockchain, state channels, and client-side validation systems, they are distributed systems. So it's quite unspecific part of the characterization of RGB. So we need to specify it and narrow it down. So unlike, for instance, state channels, it is a fully asynchronous system. because state channels were synchronous. It is because of that it is network fault tolerant, and it achieves consensus by utilizing special form of finality proofs using single-use seals coming from proof of work consensus of underlying Bitcoin blockchain. So that's the definition of distributed part of the RGB computing. The RGB is also a partially replicated system because each participant and actor has a partial view of smart contract state. The whole state is a DAC, and each participant do not have a full copy of the whole DAC. And this is very different from the blockchain environment, where all participants should have the full copy of the blockchain. So that's an important qualifier of RGB computing, that it is partially replicated. And in Lightning Network, you don't have a state replication at all. So basically, again, it's in Lightning channels, because in network, you have a map of network, there is a state replication and eventual consistency without consensus. And in RGB, we don't have we have a full consistency because we reuse consensus from the blockchain layer, but we have a partial replication of the state. And the interesting part that RGB is an indeterministic computing, meaning that the actual evolution of the smart contract itself, it is affected by participant decisions and proof of work randomness. So it's not deterministic state machine. And finally, of course, RGB is a state machine because we have a state and we have a state transitions. And with all these properties and with what I will be describing later, potentially we can say that the RGB smart contract as a whole may be equivalent to universal Turing machine. And we will analyze this property in details a bit later. And this specific computing model of RGB smart contracts we call PRISM, because PRISM, first of all, is something that creates the spectrum of different colors, and RGB is just red, green, blue, and also because it's acronym of partially replicated indeterministic state machine, PRISM. That's how it was created. This term was coined. Summarizing, the smart contract operates within constraints immutably defined by schema and previous contract history, because we commit to the schema and contract genesis, and we commit to each state transition into Bitcoin blocking. So we can't change the used schema or contract history after the state transition was created and the appropriate commitment was mined into Bitcoin blockchain. So the smart contract constraints are immutable. Each of the state transitions is partial because each state transition affects only part of the smart contract state. And each state transition is equivalent to a finite state machine operation. So it's not Turing complete. Each state transition is not Turing complete, first of all, because we have a bounded computing, just to prevent any possible forms of attacks. We have a very strictly bounded form of computing with AluVM, and we also have a schema, which actually the rules of the schema are not Turing complete. Having said that, while each state transition is not Turing complete, the whole contract may have countable but infinite number of states, because you can compose the DAC with a multiple state transitions, and schema limits you from the way you compose the graph, but you may have a schema that allows you to create a Turing complete RGB smart contract in which each state transition is not Turing complete. So it's basically RGB combines the properties of Turing completeness at the level of the whole contract and non-Turing completeness at the level of individual state transitions. I can graphically represent that in that way. So each RGB state transition which is executed as a code of AluVM or validated against schema, is a finite state automata, which is not equivalent to the Turing machine. RGB contract as a PRISM computing potentially may be equivalent to Turing machine. And Bitcoin script, which is also used by RGB smart contract validation, and which is stack machine, push-down automation, is not equivalent to Turing machine. So RGB smart contracts are computationally bounded at each step of its evolution, at each state transition, but should be equivalent or may be equivalent to universal Turing machine as a whole. Oh yeah, and actually it wasn't the last part of the presentation. This is the last part of the presentation where I just like to recap different terms which we were using throughout the presentation and create a ground for the next talk will be in 2 weeks from now. So to summarize, what components of RGB smart contracts exist? There are schema, which defines constraints for the state machine. There are nodes, which are nodes of the directed acyclic graph of the performed history of the smart contract. There are anchors, which are proofs of the state transition validity, and these anchors linking the RGB smart contract to the consensus layer of blockchain. And they do that by, they bring these two worlds together by containing two components. First of all is the single usil external witnesses, which allows you to prove that the single usil inside the blockchain was closed correctly, and the commitments to the state transition under multiple smart contracts, which committed to the single blockchain transaction. This links to RGB, and the first links to blockchain. So anchors put these two things together in one single data structure. And finally, there is a Bitcoin blockchain or Lightning channel state backed by blockchain, which is not part of the RGB contract itself, but which is crucial for the validation of RGB contract. And the Bitcoin blockchain and Lightning channel transactions control who can perform state transitions, because state transitions can be performed by only those who can spend the certain output of a Bitcoin transaction, and it enables consensus over the whole distributed state machine of RGB by reutilizing proof of work consensus from Bitcoin. We were talking a lot about schema, and I'd like also to recap what schema does. Schema allows you to answer on the following 6 questions. What kinds of ownership rights exist inside the smart contract? Ownership rights or state assignments? What kind of publicly executable rights exist? I will be explaining a bit later, because in RGB smart contract, I was saying about ownership rights, where you have a state assigned to a certain UTXO, and this do not allow a contract to have an arbitrary external participants. You always have a very well-defined set of participants, basically those who can spend those UTXOs. However, in certain cases, you may need to allow external parties, potentially not owning any of Bitcoin transactions, to participate in the smart contract, in RGB smart contract. And this is done by defining publicly executable rights. So you can say that anyone in the world can extend a state in this specific way. And this is part of the schema. This definition is the part of the schema. For instance, it may allow you a distributed issuance of certain tokens basing on the transactions in Bitcoin blockchain. So for instance, you may create an arbitrary transaction, but inside that transaction, you will have an output locking certain amount of Bitcoins in a certain way using specific predefined script template. And then you put the proof of the existence of this UTXO into a data structure called state extension. And you can link this data structure to contract genesis. And by doing that, you can actually issue something that is backed by Bitcoin on the chain. And this is a public state extension. You don't have to be a participant of the RGB smart contract to do that. And you get a property of decentralization that at the schema level, you can allow other participants to non-participants of the RGB smart contract to become a participant of the smart contract and non-permissionable way. So that's why we have another additional to own it rights. We have a publicly executable rights inside the smart contract. Next, the schema defines what kinds of contract metadata can be defined by the contract. And contract metadata, it's the data which are not owned by anyone. It's certain metadata which is generic property of the smart contract or specific state transition. Next, the schema defines which types of state data might be assigned to certain owned rights. The structure of the state data, the nature of them, is it integer, float, string, is it a public key or something else? So this, the type of the state data is also defined by the schema. Schema also defines how the state data allowed to change with the state transitions. And the schema does that by utilizing special scripting using the AluVM virtual machine that is highly deterministic and fault and exceptionless. And this virtual machine takes the state transition state, previous state transition state, and the newly created state as input, and it produces just true or false as a result of validation. And the script, you create the scripts that does this validation. For instance, it compares that the sum of the inputs is equal to the sum of outputs. So you do not inflate this total supply during the state transition. And you call that as a script for AluVM, and this script is executed by AluVM, and if there were no inflation, it produces true. If the sum of inputs is not equal to the sum of outputs, it produces false, which fails the validation. And these scripts, they are also part of RGB schema. And the final thing, the most complex and the probably important part of the schema, is you define which sequences of state transitions and ownership rights are allowed. For instance, you can create very advanced forms like, first of all, with a schema, you define which types of rights exist. You can say that there is inflation right, there is a token ownership right, there is right to burn the token, there is right to rename the token, and you can assign all these rights to different entities. And then with the schema, you define when you do the inflation, which state can be updated and how the state should be validated, and which metadata should be attached. If you're renaming the token, you define that while you're renaming the token, you cannot create an inflation, and you need to provide metadata about the new token name. So this is actually the definition of the rules, how the DAC of the state history of RGB smart contract should evolve, and it is the main and the most important part of the schema. How the schema is written? The schema is written in a functional way. So it basically declares types for metadata, state, owned rights, public rights, and possible combination of the above within state transitions. And then it provides state validation functions, which are run by AluVM, which takes the state as an input and produce the validation result as output. And these functions are provided for each of the state types and each of the ownership own state types. Additionally to the schema, which is basically can be used by multiple RGB smart contracts. So you can create a schema for fungible tokens. And with RGB, we will be releasing the schema, which we call RGB20, which is the result of 2 years of our work on finding the best and most secure way of structuring the token-based smart contracts for fungible tokens. But this RGB20 schema can be used by anybody who would like to issue a fungible token. But nothing prevents people from creating an alternative implementation with the different properties. So schema is something that may be shared by multiple smart contracts. But when you create how you create the smart contract itself is by issuing a genesis. So within the smart contract, you have two types of nodes. The first one is the nodes that generate new state data. And the second type of nodes are the nodes which change or updates the state. So the state is generated with a genesis, which actually the first node of the RGB smart contract. And you can add more state data with the state extensions, which I was just several minutes before explaining as a way of creating decentralized issuance or other forms of public state extensibility. And you update the state by creating a nodes called state transitions. And each of these RGB smart contract nodes consists of these parts. Each of the nodes may have a metadata. It is not ownable part of the state. It may have assignments, which is owned part of the state. And each assignment consists of a type of ownership rights taken from schema, definition of single-use seal that will own that specific state under this right type, and the data, state data, which are optional and which may be absent, or if present, it may have form of homomorphic zero-knowledge proofs, like Pedersen commitment for creating confidential amounts about the amount of asset that somebody knows, or it can be just arbitrary data which are not homomorphically encoded, but still can be made confidential throughout the history because we are using a hashing of this data for the contract history. And finally, additionally to metadata and assignments, each smart contract node, so it's not smart contract state, it's smart contract state inside contract node, may have a valencies. Valencies is actually these public rights coming again from schema with no state. It just points indicating that external parties to the smart contract can extend the state of the smart contract with this state extension. So that's why they're called valencies. It's an opportunity for anybody to participate in the extending smart contract state. And of course, it's kind of thing that most of the RGB smart contracts will be missing. For instance, RGB20 schema doesn't have valencies. It's not no use of them there. And the RGB21 NFT schema doesn't have valencies. The valencies will be used only in the schema for Bitcoin-backed asset issuance, for instance, which will be not an RGB20 schema, a specific dedicated schema type. And this is the chart that demonstrates how which type of state data different type of RGB contract nodes may have. So all of them have metadata, may have valencies, and have assignments. But the genesis state extension and state transition differs in which part of the state data they allow to update. So genesis, it just creates states. It is state. It can't update state because no state exists before genesis. State extension can use valencies defined by other smart contract nodes, but it can't close any single-use seals. And closing single-use seals in RGB we called extinguishing assignments. So it can't extinguish any existing assignment. On the other hand, state transition, it can't use any valencies, but it has to close certain single-use seals. And by using single-use seals, it will invalidate the previous state. It will extinguish assignment of that previous state and define a new state with the newly created assignments inside that node. Final two slides. How all these nodes and RGB smart contract data can be packed. They are packed into structures which we called RGB containers. And this container serves different purposes. We have four main types of containers. The first container I was already talking about is a stash. And stash is all RGB contracts. It can be multiple contracts plus schema. And the stash includes all RGB contracts and schemas owned by a user. And because RGB contract is always a partial state, so it's actually a partial state data, and nothing prevents you actually from putting into a stash an alternative histories. For instance, if you are doing, for instance, if there was a reorganization in Bitcoin blockchain, the organization in Bitcoin blockchain would not invalidate stash. And basically, you will be able to add an updated version of the state transitions after the blockchain reorganization into stash, and there will be no merge conflict created. The second part of the RGB container is consignment. And consignment is the data structure that is used when you transfer certain state from one party to another. For instance, you send some coins or tokens from Alice to Bob. And then when Alice sends some tokens to Bob, she creates this consignment and passes it to Bob. And the consignment includes a single RGB contract state and the whole history of this state from genesis to the endpoints, which are actually a state owned by Bob. All other branches are hidden from Bob. They're cut from the history, and the data related to the branches are made confidential. So Bob doesn't know any other part of the history than the history that leads to to the state that is owned by him. And the consignment is actually the data structure that is the only data structure that it is being validated by RGB. So when you receive consignment to this validation process that I was describing before, you validate the contract history from the consignment, this validation from here. And if the consignment is valid, you merge it into the stash, because you never validate stash, you validate only consignments. The third structure used by RGB is disclosures, and disclosures are fragments of data. These fragments may come from a multiple RGB contracts, and disclosure is the way how you can disclose some information to a third party. For instance, you decide, it's always your decision to disclose something, but you, for instance, like to disclose a part of the history of your state transitions and historical transfers, and you will use a disclosure for that. And you can send or upload disclosure to a public server by leaking some of your privacy. But again, if you need it for some reasons, you can always do that. And one of the main cases for disclosures is for asset issuers. If asset issuer create an asset that can be inflated, for each inflation event, the issuer creates a special state transition called inflation state transition, and then he needs to let the world know about this inflation, the publicity know about the details of this inflation, and he does that by creating a disclosure and publishing that into the Lightning Network. Lightning Network not in terms of Lightning Payment Network and Lightning Channels, but in terms of Lightning Peer-to-Peer Network. And the final structure of used by RGB contracts are data containers, which are blobs of supplementary data, like media used by non-fungible tokens. And this data container is specific to a given RGB smart contract, actually to a given RGB smart contract node. And for instance, you can, if you are a content creator, you can pack digital representation of painting or a song or a book or whatever you create as this data container, attach it to a smart contract issued under RGB21 schema, and distribute it through a Lightning Network. So that's how you transfer the parts of the RGB smart contract state between different parties, 4 ways of doing and keeping the information. And the final part is that the state update, as I already said, is called extinguishing of assignments, because you assign state to the UTXO, and then you extinguish this assignment by spending that UTXO. And state is invalidated on a per assignment basis by the fact that you spent certain UTXO that had a previously defined state as a single UCL. And the single useal must be closed over a message, which is actually the Encore data. And this Encore data will contain a commitment to the newly defined state in a newly created state transition. So that's probably the most complete up-to-date overview of how RGB smart contracting works. I understand that it still may be quite complex, but my aim was to provide the most complete information for people to understand RGB as a system with all of its components. And if some parts are difficult, I just advise to watch through the slides or from the recording once again. And over the future developer calls, I will be from time to time creating more maybe simple and maybe detailed explanations devoted to certain aspects of RGB as a system. So that's all on my side, and probably we can get to the questions and answers.
Excellent presentation. Thank you. Thanks. So, can I go first with the questions?
Yes.
Can you switch to the one before last slide?
This one.
Yes, this one. So, question number 1, you said that stash can contain alternative histories because of
Yes.
the reorg and stuff. Knowing the difference between double spend and reorg, again, knowing the difference, how can you explain still how would the node that accepts, for example, the transaction with the stash, with the asset or something, verify which history in the stash is the true one?
Well, you have to understand that stash is not something that necessarily valid. The stash is just a garbage collection. It's kind of you keep everything that you just can't keep, and it may contain invalid state, whatever you put in there. It's not the point. When you work with the stash, it's not the point of time when you accept something new to the state from external party. So the only case when you do the validation of your own state is when somebody sends you something, and transfer is always performed as a consignment. And what you do is you validate consignment, and consignment must be valid. And if you will maintain your stash by just adding to the stash a valid consignments, your stash will be also valid. But nothing prevents you from adding to the stash arbitrary data. Nothing prevents you. I'm not talking from the terms of user. I'm talking from the terms of developer for RGB. So as a developer, nothing creates you from creating a wallet which will add invalid consignment into the stash. And once you do that, it will be part of the stash. But that means nothing, because you wouldn't be able to transfer this state further, because the next actor, he will be validating your consignment and it will be invalid. So basically, you will just have an invalid view on your own smart contract, and that's all. And if you'd like to prevent the invalid view on your smart contract, you just don't merge invalid consignments. You will just not merge arbitrary disclosures. And that's all. And if the stash, but again, the validity of the stash, there is no, actually, stash can be valid or invalid. It's just a garbage collection. And when you create a transfer, what you try to do is you reassemble the history by taking the data from that garbage into a valid consignment. And it doesn't matter how many garbage the stash contains, unless you are able to construct the valid history out of this garbage, throwing out everything that is not required for this single valid history.
Oh, okay.
Does it explains the idea?
Yeah, especially the last 2 sentences. Yes, they do. Okay, perfect. Thanks. Next.
On your hard drive, you can think about stash as a hard drive. You can put to hard drive whatever you want. And if you have important data, these data are on your hard drive, and they're still important and valid, notwithstanding the fact there is a plenty of garbage other data on the same hard drive.
Mm-hmm. Yeah, okay, that makes sense. Perfect.
Yeah.
Good. Also here, regarding the disclosure, so
Yeah.
publishing the information, if you need to do the inflation thing with the asset, so you need to publish the information on inflation to the Lightning Network. And yes,
Well,
it does compromise. Yeah, so my question is, if you're publishing it to the Lightning Network, so the disclosure is not that bad for your privacy because you are not explicitly and openly publish the information to the Bitcoin blockchain, which is opened and like traceable without like
I will
without
probably
problems.
do a separate presentation on these types of data structures, because it's very important and quite complex topic. Because I was really trying to be brief, and by being brief, I skipped a lot of stuff. So regarding the disclosures, first of all, when I said you can publish it into Lightning Network, I meant that one of ways of making disclosure available throughout public is to publish it into a Lightning Network. Once there will be an extension to Lightning Network, which we call Bifrost, that will be a special protocol that allows distribution of that type of information across the Lightning Network. But disclosures itself at the level of RGB, they are unrelated to Lightning Network. You can publish them, but whatever, by BitTorrent, by just printing on the sheet of paper and sticking to your wall or in the shop or whatever you want to. It's just the RGB doesn't care the way you publish the disclosure. It's the first step. The second step is that you create disclosure when you want something to disclose. So disclosure by definition is the privacy leak because you disclose some private information. That's the whole point of the disclosure. Why you would like to do that is completely outside of the scope of RGB. Maybe you're just a crazy person and you would like to live a public life. Or maybe you are a set issuer and you would like to provide the details for a public audit of how you issue, how you increase the supply of your assets. Or maybe you just guy who believes into government and would like to disclose his funds for the tax authority. I don't know. You can be whatever crazy you like to. But that's the point of disclosures. You disclose your private information, which means you leak your private information. Why? It's not the question to RGB, it's a question to you.
So basically, it's the question to the use case that the person is working with.
Yes.
Okay. Can you go to the slide 16-ish, please?
This?
Yes, I think it was 16. So you said that a person needs to can verify the proofs against both blockchain and you said both blockchain or state channel. So
either.
both.
Well, no, not either. It depends. If you put RGB on top of blockchain against blockchain, if you put RGB on top of Lightning Network against the state of the Lightning channel, it's what you're working with. But if
So
you are even verifying against the state of the Lightning channel, you still verify the Lightning channel against blockchain anyway.
So basically, it just depends on which level you're operating RGB, as a second layer or as a third kind of.
Yes. Okay. Yes.
Okay. Also, to verify one thing, you said that nodes in RGB, smart contracts in RGB, they are absolutely separated, but they still
informationally separated. Probably the proper term.
So they cannot communicate with each other, right?
Yes, you can't validate one smart contract against the smart contract at the level of RGB itself. Nothing prevents you from creating some system on top of RGB, which will do some cross-validation, but it will be a system of top of RGB.
Okay, but on the same In the same time, on the same time, you can compose a couple or like several of RGB smart contracts and stitch it to one UTXO.
It's
they
not,
can-
you compose them, so they are still informational separate. You
Yeah.
commit to a set of state transition under different smart contracts inside a single anchor and a single transaction. But when you validate that, there is still full informational isolation, and you don't see which other RGB smart contract had commitments under this specific anchor. So I will try to put it into other words. Let's say, because you have to maintain your the size of on-chain data as small as possible. So in most of the cases, the normal users of RGB, they will own multiple assets or multiple rights under different RGB smart contracts. Like, for instance, I can own some stablecoin, some shares of some company, some NFTs, and so on and so forth. And at the same time, my UTXO set is very small. It could be, in most cases, just a single UTXO that I have. For my current account, for instance, or several UTXOs. The set of UTXOs that I own is potentially much smaller than the number of RGB smart contracts that I'm participating in. And this is why I should have an ability to assign state from multiple contracts to the same UTXO. So on the same UTXO, I can have shares, stable coins, NFTs, whatever I need to. The problem is that when I spend this UTXO, I invalidate the state of all of those contracts. If I'd like to transfer just a single asset, let's say stablecoin, I still invalidate state of the NFT and the shares at the same time. And I basically have to create, and because when I transfer stablecoin, I still have a change that I have to pay to myself. I'm spending this UTXO with a transaction that have a single output, a single input, and single output. The single output gets all the Bitcoins from the previous transaction. And I use this single output to put in all my change of the stable coins, and also create so-called blank transitions for NFT and for shares. And this blank transition again assign all of the NFTs and shares to the same UTXO. So basically, I create a bunch of state transitions for each of my smart contracts, and they all goes into commitment into the same single transaction. And what Encore does, it assembles the commitments to each of these state transition under different smart contracts into a single data structure. It does this commitment in a zero knowledge way. And when I will be doing verification, for instance, for my stable coin, I will even do not know how many other RGB smart contracts were participating inside the same Bitcoin transaction. Not saying about that, I would certainly not know what were those smart contracts, unless I will do a disclosure. Hopefully that explains something.
Kinda, yes. I will need to digest it once more on the recording, but yeah, a lot of details. Thank you. So probably no questions from me. I did have one question that we already answered probably like 3 times on the dev calls, but I'd rather stick to the current topic right now. So guys, do you have any questions? If you're shy or you have any reasons not to speak up, just send the message to the chat. Okay, so there is one question though. I believe that the RGB20 and RGB21 contracts written in Rust already existed before AluVM. Will there be a re-implementation of both in AluVM scripts?
Well, AluVM doesn't implement the smart contract, and I think that maybe in the next presentation will be about writing RGB smart contracts, where I will showcase how you actually create smart contracts, and not in terms of definitions like this is a node, this is a schema, but it's a practical example, because without that, it's really hard to grasp what is RGB smart contract in practical sense. So AluVM, you not write a schema in AluVM. You not write RGB smart contract in AluVM. Let's say that way. RGB smart contract starts from Genesis, and Genesis always use certain schema. And schema becomes part of the smart contract, but schema exists originally outside of the scope of smart contract, any specific smart contract. So there are two different things: how to write schema, which may be used by future smart contracts, and how to issue a smart contract under certain schema. So when you write a schema, when we are talking about RGB20 and RGB22, we are talking about schema because it is a schema name. And the schema is a binary data structure. It's not written in Rust. It's a binary data structure encoded using RGB schema encoding. And when you have it in binary form, you don't need any implementation of it. The RGB is the implementation of which can parse any RGB schema. But because so in this term, nothing changes. The second part of the answer, because you can't you're a human being, you can't write a binary schema with a bytecode. You need certain way of creating this bytecode. And currently, I'm using Rust for, I created a domain-specific language inside Rust for defining schema, and then Rust compiles this schema into a binary representation. But this actually is not part of RGB core itself. It's just a way how you can compose this binary schema. And again, thus nothing changes here. It will change when we'll have time to, or somebody else will do a language for more high-level language than Rust itself to write schemas. For instance, I have a draft of language called Contractum, which may simplify these things. But again, it's not related to AluVM or whatever we discussed today. And the third part of the answer is that we are still talking about schema. We are not moving to Genesis yet. It's about AluVM. So where you use AluVM? You use AluVM to write specific scripts inside the schema definition that will validate certain state. And again, there is no language for doing that today. You just need to write a bytecode. I have a AluVM ASM assembly language, which is again implemented as Rust domain-specific language, with which I can write simple AluVM scripts today. And this is actually probably the answer to the question that we were asked, is that the fact that before existing RGB20 and RGB21 state validation scripts inside the schema were implemented as embedded procedures. And these embedded procedures were actually hard-coded into RGB core validation logic. Like it will know that once you meet this type of public right, you have to sum the inputs, sum the outputs, and make sure that they are matching each other. And this was a real limitation, because if you would like some other logic of validation, you wouldn't be able to create it, because you can't modify RGB core. And that's why the AluVM was introduced. And with AluVM, you basically move this validation logic into AluVM script, and you can write whatever AluVM script you want, or any kind of custom validation. And this is what changes in RGB20 and RGB21. So with next release of RGB, I will have to embed the bytecode written for AluVM for the validation procedure as a part of schema. How I will get this bytecode for AluVM validation? Well, I will rewrite it in AluVM assembly at the very low level and make it part of the schema. So that's how it's gonna work. Probably not clear enough.
Okay. Well, maybe some more practical call would be indeed.
Yeah,
Nice.
yeah, probably. So I think we should do the call where I will be demonstrating how these smart contracts are written.
Yeah, just maybe just a couple of slides to just show, to describe in pictures what you just said, and then absolute like practical stuff.
Yeah. Okay.
Yeah, Tricola said that the part 3 of the answer make it clear, at least. Good.
Okay. Sorry, I'm trying to make as precise answers as possible because I know that many people may listen to the same recording afterwards. And quite frequently, people are just taking the words out of context and saying, you said that or you said that. No, I meant different things. So that's why I'm trying to be as explicit, as detailed as possible when I'm answering some question.
The vocabulary of my question was not precise enough. That's okay.
No problem. One of struggles which we had with RGB is that you have to create there are so many things inside RGB which has no names, and you have to invent those names, and then you have to somehow explain these names to people, like assignments, consignments, stashes, disclosures, public rights, owned rights, and so on and so forth. It just have no equivalent in the chain world, in the Lightning world, anywhere. And it's really hard to explain RGB because of that. Single-use seals, witnesses, external witnesses, and all. It's just crazy. Probably, but we already have some glossaries made by Olga, and quite detailed glossaries, but we still have to extend that. So I think that the total vocabulary of RGB, which will be specific to RGB only, will exceed 100 of new terms.
Yeah, that's true. Very. I mean, even now, a lot of people think that RGB is a sidechain, or I mean, even the comparisons and the questions on the comparisons with sidechains, with drive chains, with any type of chains, are sometimes so. They are. I mean, I understand the honest attempt to understand RGB, but they are put. The questions are put in terms of the systems that cannot be applicable to RGB. Like you cannot describe RGB in terms of Bitcoin 100% or in terms of Lightning. This is why when I get some questions in chats, for example, or on Reddit or on Twitter, it puzzles me very much, because when you use even the client-side validation, like words, people still like don't understand what exactly you mean, and they start pushing their own narrative instead of just absorbing.
Yeah, that's very difficult. That's very difficult. It's actually typical example of Gödel theorem is that with any axiomatic system like you're using in Bitcoin or Lightning Network, there will be a certain stuff that you wouldn't be able to explain and prove inside that axiomatic system, which will be still valid. So pretty much the same applies to RGB. You can't explain and prove certain things about RGB by just using Bitcoin and Lightning Network axioms. And that's the most complex part. So I was trying to, this time I tried to put it into perspective of computing model, how the RGB computational model fits the other computational models from Bitcoin, from blockchain, from state channels, and compare them. And maybe this will help somehow. I doubt so, because it's still very complex, but still another try.
Well, even for me, I understand that now I can answer many questions better because of the first couple of slides, which describe the difference between client-side validation and client-side data. Because one of the stones that I constantly bump into is people actually like merging those things into one, and they don't understand this. And this is why they don't understand the difference between RGB and like sidechains or many different projects in Bitcoin world. So that was very helpful, at least for me.
Well, let's let's try to, let's see how it will work out. I still think that it will not be sufficient to explain what we're trying to explain, but another step forward that goal.
Yep. Okay, guys, it's been quite a while. So does anyone have any questions? Yes, no, yes, no. Any type of answer can go to the chat.
Or just speak using microphone.
So maybe one last question then, and we can wrap this up. Or if guys, you would some questions that you would come up with, you can put them in the chat. So again, we already talked about it, but maybe it can be still useful to repeat that again. What can serve as layer 1 for RGB? Because some people start asking me about whether the layer 1 can be Lightning. Someone asked me about layer 1 as Bitcoin sidechains, so not Bitcoin itself, but Bitcoin sidechains. Can Bitcoin sidechains be used as layer 1? Bitcoin forks, Ethereum-based blockchains, rootstock, and it's like thousands of many different options there. And maybe we can answer once and for all.
We are in the IT world, and that means that everything can be combined with everything else if a sufficient effort is put into. So you can probably do whatever you want. So we can narrow this question down by two things. First, what are we doing? And we are doing client-side validation in the context of Bitcoin ecosystem, wide Bitcoin ecosystem we call LNPBP stack. We are not doing it on Monero, on Ethereum, anywhere else. It doesn't mean that you can't do that. Probably you can do that. How you can do that? I have no idea and no intent of spending my time into investigating that stuff. So if somebody is interested, go and do that. But we are doing client-side validation in the context of LNP-BP stack. It doesn't mean that it's not possible outside of it. Probably it's possible. No idea, no interest in that idea. That's first. The second, RGB is a specific form of client-side validation with the properties we just discussed through this presentation. And this RGB is a smart contracting system on top of Bitcoin and Lightning Network by definition. So you can't put RGB on top of Ethereum because by definition, the world RGB is reserved to the client-side validation smart contracts on top of Lightning and Bitcoin network. So what you can do on top of Ethereum is to create another system on top of Ethereum, which will be a client-side validation system, but you can't use it, name it RGB, because by definition, it's a different system from RGB. Like we reserved this name for Bitcoin, LNPBP ecosystem. So name that whatever, plasma, RGB, cache, stash, whatever you want. But it wouldn't be RGB anymore. It will be another client-side validation system on top of... Sorry?
RGB Satoshi Vision.
RGB Buterin Vision, whatever.
RGB Buterin.
But again, it's not RGB. It's some other client-side validation system on top of other stuff. How to do it? No idea. Not interested. Can RGB work on top of sidechains? Again, let's differentiate client-side validation and RGB. Client-side validation can work on top of sidechains. As I said, nothing prevents you from doing open timestamps on Liquid. RGB specifically today works only on top of Bitcoin and on top of Lightning Network. May you make it working on top of Liquid? Theoretically, there is no limitation from preventing you from doing that. Practically, you have to sit down and write that code, because I'm not going to do that. So if you will write that code and create a pull request into RGB, and it will be a good pull request, we will merge it, and RGB will be working on top of Liquid. But before this event happened, it's not working on top of Liquid. I hope that answers this question.
Yeah, basically the same thing can be applied to Rootstock, as far as I understand, because they have Bitcoin as a base layer, and then they're trying to do Ethereum contracts on top of it. So in theory, client-side validation can work there, but RGB cannot, for the reasons that you just mentioned.
I would say that the Rootstock sidechain falls into a very different category than Liquid, because Liquid uses UTXO model, and it's really easy to actually make RGB working on top of Liquid. While Rootstock uses account-based model like in Ethereum, and I have no idea how to make single-use seals work on top of account-based blockchain. And they have no desire of studying this field. So you can't just create a pull request to RGB core, adding support to Rootstock, because you have to rewrite basically the whole RGB, and it would not be RGB anymore, and not the UTXO-based single-use seals anymore. It will be just a completely different client-side validated system.
Nice, thanks. My favorite question: do you have any further insight into when RGB will work on Lightning?
Let's define what you define by working. When you will be able to send assets to each other, when it will be ready. When it will be technically working on Lightning, it's already technically working on Lightning. So we are in the middle of getting the system working on Lightning to the getting end user consumer facing products using RGB on top of Lightning. And when this process will finish, it will finish when it finishes. I have my best hopes that it will have finished soon. All the history proves that it doesn't happen that soon as I wish to, because of practically many obstacles. Like I spent the last 2 months fighting the bureaucracy system of Switzerland, and regarding my permits and all the stuff. So if there will be other complications, I just can't predict, which I can't predict. So it will postpone it even further.
On which Lightning implementation? On our Lightning implementation?
On LNP node, yes.
The LNP node.
Sorry?
I said on LNP node that we have had for many months.
Yes. Well, the question is like, it's an open source project. If somebody wants to make it working somewhere, like on LND or C Lightning, just code the stuff. Like, we are all people which develop RGB, spending our own time and funds and everything. So we are just doing what we can. Other people can do what they can. So basically, the only answer to the questions when RGB will be doing something is then when somebody will do that. That's the only answer.
Yeah, I've been receiving quite a lot of questions of LND support of RGB, and as I think we discussed it on the last call, on the previous one. So this is not the question to us because we do not have any capacity to do that, and we're focusing on different stuff. And it's a question more to LND team. When it's like the business decision of their team first and foremost to add RGB support or not, and the work should be done by them eventually, not by us. Still, we are open for cooperation, but again, they should be the second party that we might cooperate with. Not it's like a two-way street. Yeah, the more detailed answer to this can be found in the previous call agenda and recordings if you're interested. Okay, guys. So 2 hours, not bad. Any more
Not as
questions?
bad as I was expecting for
Not
70
as
something
bad.
slides.
Not as bad, not as bad. So I think we can wrap this up for today. All the presentation, the audio recording, and the video recording would be uploaded online. So just look up stay tuned in the Telegram channel and check out the RGB FAQ from time to time. Don't forget to subscribe to our YouTube channel, just not to miss the updates and everything there. What else? Yeah, we also have Twitter and another Telegram channel where we just post updates, new library releases, and all that. You can also subscribe there.
And RSC chart for any technical, in-depth questions and topics. Hello?
Well, thank you for your time to do the developer calls bi-weekly, right?
Right.
So guys, from now on, we are switching just in order to focus more on developing, on coding, and not on talking. We will do our developer calls once in 2 weeks. So the next one will be in 2 weeks, not the next week. Again, I will post details in the Telegram chat. So thank you for your time again. Thank you, guys, and see you soon. Bye-bye.
Thank you, everybody, for joining. Bye-bye.